Hi everybody. So we're going to start with the worksheet that I gave you guys in class, and if you weren't here or whatever, just kind of follow along because every single new screen is going to have a blank free body diagram, sort of like this is. Here's the situation, and what you're expected to do. Pause it and then work on it, and then hit play, and I'll go through it with you. And if you were here during class, here's how you do everything that I asked you to do. So our first example is we've got an 8 kilogram block on a string hanging from a rope. So we know that we've got at least one force, and that is going up, and that is the force of tension. And then we also know that that block is hanging down because of the force of gravity. So all we have to do is figure out the magnitude of those two forces. And we know we've got an 8 kilogram block. If you remember, F net equals ma. The acceleration that's causing this block to hang down is from gravity. So the F on the block is the mass, 8 times gravity is 10. The acceleration due to gravity is 10, which means the force of gravity on the block is 80 newtons. And we've got 80 newtons going down and a net force on the block of 0. We have to have 80 newtons up. So we can actually call this negative 80 and the tension would be positive 80. And both of these added together would give you a net force of 0. So remember, as we go through all these, all of the forces have to add up to exactly 0. Second one, we've got a 15 kilogram book resting on a table. So once again, anytime we start a free body diagram, you always are going to start with a dot. And our forces are gravity. And this time we've got a surface. We've got either a floor or a table or a wall. Those are our three typical surfaces that we deal with. And those surfaces make normal force. So all we have to do is figure out what the gravity is and what the normal is. 15 times 10 is going to be 150 because gravity is going down. And the normal force is going to be positive 150 going up. Next, we've got a 20 kilogram book going into a corner. So here we have a wall and we have a floor. So we're going to have two normal forces, assuming that we need to. And I'll tell you what, you'll see what that means in the next one. But here's our free body diagram. Here's our dot. And I'm going to start getting a little better with my arrows here. We're going to have one going down, and that is from the force of gravity. We are going to have counteracting that one going up, and that is going to be from the normal force, from the floor. And I just call it FNF for the floor. Now we're being pushed in to the wall by the applied force, and that applied force is 50 newtons. Which we can deal with in a second. But we have an FA. And for giggles, let's just put it the 50 newtons in. And if we're going into the wall, but we're not actually accelerating into the wall, there has to be some sort of force pushing us backwards. And because that force is from a wall, remember we call those forces normal forces, and I'll call that a normal force from the wall. So we have two normal forces, one from the floor and one from the wall. We also have gravity applied. So the gravity, if we remember, 20 times 100, 20 times 10, that's not going to change. So we're going to have 200 newtons as our gravitational force. What we're going to have for the normal force from the floor is the opposite of that. Remember, the y's, the verticals, have to cancel out. So if we've got a negative 200 on the bottom because it's going down, we're going to have a positive 200 going up. So the book isn't going, or the box or whatever it is, isn't going to accelerate vertically. It also can't accelerate horizontally. So if we've got 50 newtons going to the right, we have to have exactly 50 newtons going to the left. And when we have left, we say negative. So you got negative on the bottom, negative going to the left, positive going up, and positive going to the right. So this is a typical situation where you're being forced into the floor by gravity and forced into the wall by the applied force. And this is not true in this particular case. And we sort of did this in class the other day where, there were a couple of people that were sitting on a chair and we talked about, well, you're being forced into the chair by gravity, but now if I push you more, the chair has to work harder to keep you up. And that's going to cause an increased normal force. So this is exactly what that's going to look like. Let's get our dot going on here. And let's just talk about the forces we've got. We've got one from gravity, and then we're going to have another one from the applied force. And then going up, we're going to have something that's going to counteract both of those. Now, there's no force going into the wall, so there doesn't need to be a force coming from the wall. So if you see here, all of our forces are vertical. Let's start labeling them now. So we know the FG and the FA. And I guess this one has to be from the floor, so we call that FN. So the gravitational force is never going to change. 20 kilograms times 10 is going to be 200 newtons going down. And the applied force we see is 20 newtons. So we're going to have another negative 20 newtons. So if we've got grand total 220 newtons pushing down, the normal force has to push up equally on that 220 newtons to give us a positive, I wish I could write better, 220 newtons. I hope that makes sense. You just take these two and add them going down, and you have to take the opposite of that and have it go up. So these are kind of warm-up exercises. They shouldn't have been that terrible. We are dealing in 2 dimensions, but you don't need those triangles yet. And then this is where the proverbial rubber meets the road here. These are where things start to get a little complicated. And you have to remember, when you've got forces on an angle, we can turn them into triangles because we typically have to get vertical and horizontal components, x's and y's, from these forces. So I'm kind of going to, as we go through all of these, I'm going to do the free body diagram over here. And I'm going to try and do the calculation sort of in the middle to show you the line of thinking that you should have. And I'll also be drawing all over the picture here. And I'll actually try and draw in the picture in a different color to show you what I'm thinking. So I know I've got 50 kilograms going down. So you know what? Let's just start with the free body diagram itself. Let's identify all the forces. Don't worry about the numbers yet. So if we got 50 kilograms going down, that's going to be an FG. And we're going to have 2 tension forces. And we know that those tension forces are at 70 degrees. So the only number we know here besides the 70 degrees is 50 kilograms, which is going to make the gravitational force 500 newtons. Now here's where I start thinking. If I got 500 newtons going down, I know I need 500 newtons going up. And I know I have 2 strings, so I have to divide that 500 newtons going up by 2 for each of those strings. So this string here is responsible for generating 250 newtons up, and this string here is responsible for generating another 250 newtons up. So instead of writing the 500 in the middle here, I can actually just write the 2 250s. And I'll get rid of this. I will go back here and I'll give you a 250 here, another 250 there. So now we've got this triangle here that's 250 newtons on one side, some number of newtons on this side, and some number of newtons on this side. But we have another piece of information we can use, and that is the 70 degrees here. And if we take this 250, oops, this message again. If we've got 250 here, we've got 70 degrees here, we know that this and this are going to make a 90 degree angle, so our 90 degrees minus our 70 degrees is actually going to give us an interior angle here of 20 degrees. So now we have 2/3 of a triangle. We've got a vertical, which is 250, 20 degrees there, and we have a hypotenuse. And what we really care about is trying to make sure that we can get that hypotenuse. Because these two angles are the same, so and we know everything's going to cancel out. All we need to know is the hypotenuse, because this horizontal going this way is going to cancel out with the horizontal going this way. And the vertical going this way is going to cancel out with the vertical going this way. So the calculation you really have to do is, and I'll try and make nicer lines for you this time. You're going to have a vertical, sort of, it's not very vertical, is it? Vertical, horizontal, or a diagonal, and something that's more or less like that. So we know this side is 250. We know this angle is 20 degrees. And we also know that compared to the angle, this is the adjacent side. So if I've got an angle and an adjacent side and I'm looking for the hypotenuse, we remember that we got to use cosine. And we use cosine of the angle equals the adjacent side, 250, over the hypotenuse. And this is where you guys might get a little confused. You might want to take 250 and just multiply it by cosine of 20, but you can't, because we're trying to get the h by itself, so you really have to cross multiply. Cosine 20 over 1 equals 250 over h. That'll give us h times the cosine of 20 equals 250. And then we still have to get the h by itself, so we have to divide both sides by cosine 20. And that will give us our h. So h, this cancels out, equals 250 over cosine 20. And that will give us a hypotenuse of 266 newtons. So this side is 266. And it's the same triangle on the other side. This is still 20 degrees, so the other side is going to be 266. So for our true free body diagram, you got FG here. I'll make this that color, and we'll go FT and FT, because we have two ropes, equals 266 on both sides. 266. And remember, the whole point of this is to really drive home the point that as you have an angle here, the tension on that angle becomes bigger when the angle gets bigger. Alright, so we're still generating, each string is still generating 250 newtons going straight up, but because we're not pulling up, we're pulling at that angle, you actually have to pull harder. And that goes back to why bridges are designed the way that they are. That goes back to why, we said in class, when you buy a really nice expensive picture, they put wire on the back usually instead of string. So I hope this really helps drive home the point. And now for my first shameful thing. On your worksheet, and I would really appreciate it if you were in one of the earlier classes that I didn't catch this on. Pause it here. And don't pause it yet, I'll tell you what to pause it. But rework this problem with the following number. My intention was to show you or remind you what happens when the angle gets really, really big. And if you remember in class, we had people pulling really, really hard on that string, and we had the weight in the middle, and we couldn't get it straight. So what I was hoping was that we would use 88 degrees in our calculation, which I drew the picture backwards. So what I'm really shooting for is we get it almost flat, which means this side is only 2 degrees, and this side is only 2 degrees, which will make, and again, here's my thinking side, which will make this angle 88 degrees, as well as this angle 88 degrees. All right? So why don't you pause it here and rework the numbers using this. Again, it's just like we did here. It's just like the last problem, but we changed the angles. Okay? So I'll wait, pause it. Please work on this because it'll help you see what I'm trying to show you. All right, I hope you finished up, and we can actually, why don't we go ahead and actually start the free body diagram. So we'll give our dot, and we know we've got 50 kilograms down, and we got two sources of tension. So let's give us a down arrow, and then two tension forces. Let's make it like it is, barely above horizontal. Fair enough? So we know what the three forces are named. We know this one is the force of gravity, and this one's going to be attention, and this one's going to be attention. And I remember in class, there were a couple of people that thought this would be 12 degrees instead of 2, and I didn't even catch it either. Because 88 plus 12 is 100 degrees, which is not flat, So 88 plus 2 is 90 degrees, so you have 90 degrees on this side, 90 degrees on this side, and then you have a flat thing. So our tension, our gravity, these are our two forces. Our force of gravity is again going to be 50 times the acceleration due to gravity, which is going to be 500 newtons. And now the adjacent sides are going to be, the vertical sides are going to be, 500 up. Because you got 500 down, you got 500 up. This side is responsible for generating 250 of it. And this side is responsible for generating 250 of it. So now this kind of gives you the framework to work through this problem. And let's give us a nice, fresh, clean triangle to work with. Let's go like that. And then we'll go like that. And then we can go like that. And we can write down what we know. We know this side is 250. We know this angle is 88 degrees. And we're looking for the hypotenuse. This is the opposite. This is the adjacent to this angle of 88 degrees. Once again, we're going to have to go cosine because we're using the A and the H. So cosine of the angle, 88 degrees, equals the adjacent, which is 250. 250 over the hypotenuse. And again, you have to do the cross multiplying, and you'll end up with 250 over cosine 88, which is actually a pretty big number. You should end up with 7,163 newtons on each of these sides. So in order to generate 250 newtons going up at an angle of 2 degrees to the horizontal or 88 degrees to the vertical, you have to kick in a tension force of 7,163 newtons on both sides. So 500 down, 500 up, but in reality it's 250 up from this side, 250 up from this side, and you're only getting that 250 up because you're pulling so hard to the side. Alright? So those are two really important questions that I want you to be able to be very comfortable in answering. Both of these, and then I'd like you to answer why you have to pull so hard to the sides to get something to go up. And the real answer is because as that angle changes, you have to kick in more or less tension to generate the same force going out. So the rest of these are a little more thought-provoking, and that's really what it is. We're starting here with a 10 kilogram mass, and we're pulling it with 10 newtons this way, but we don't know how hard we've got to pull it this way to get everything to be static. So one more time, I'm going to work calculations in the middle, and here's going to be the free body diagram. So here's our dot. And what we're going to do is we'll start out with what are the forces that we know. We know this thing is being pulled down by gravity. We know it's being pulled to the side by an applied force. And we also know that it is being pulled up and to the left by a tension force. So now what? And at this point, and you really could have done in this side, you could have done XY charts, and in this one you could have done XY charts, but you know that the X's are always going to be even and canceling out. So you're really only dealing with the Y's in these two. So this might be a decent time to actually start doing an XY chart. So let's get our x and y, and then our three forces, our Ft, our Fa, and our Fg. And we remember that they all have to add up to F net, which equals 0 in the x and 0 in the y. We really don't know too much, do we? We know that the applied force in the x dimension is 10 newtons, and it's going to be 0 newtons in the y. We know gravity is going to be 10 kilograms going down. That gravity is going to be negative 100 newtons. So that y is going to be negative 100. And the x is 0 because we're going straight down. The applied force equals 10. So now we've got to figure out what this tension is going to be. And math of math, what plus 10 plus 0 equals 0? Negative 10. What plus 0 plus negative 100 equals 0? Positive 100. So now we've got a triangle that's going to go 100 up and 10 over, which is what, there's your tension, T. Something that's 100 and 10. Can we do a squared plus b squared equals c squared? I hope so. And if you do that, you should end up with 10 squared plus 100 squared equals 10100. And you take the square root of that, and you would end up with a tension force of 100.4 newtons. So 10 that way, 100 down, 100.4 up and to the corner. So you didn't even need the angle here, which is a really nice thing about some of these types of problems. Our next problem is this particular one, and I actually screwed up. I called this 2 kilograms. It actually needs to be 1.5. And if you did this and you were wondering why some of the numbers weren't working out, it's because when I made this problem, I messed up. So it happens. If you did this, it should explain why you've got a little discrepancy in the y dimension. If you didn't do this, ignore it. Try it with 1.5 and let's kind of work this together. Again, I've got multiple different forces. I'm wondering how hard I have to push to the right to keep this 1.5 kilogram block on this thing when I give it a tension force of 30 newtons. And we got to keep it not moving. So let's give ourselves our dot and let's talk about the forces that are applying on here. We know one going down is gravity. We know one going to the right is an applied force. And we got one more going up that way, and that would be the tension force. There's really nothing else working. We've got no surfaces, we've got no wing, we've got nothing else. So we can go ahead and label these as FG, FA, and FT. And we're sitting in the same place where we were before. We really should probably just make an XY chart to get everything sort of hammered out here. So we got FG. We've got FA, and we have FT, and then we know they all have to add up in F net and have an F net of 0 in the x and 0 in the y. So the FG, well, I'll come back to the FG and why we had to change it. But we know that the FT is 30 newtons, and we know we've got an angle of 30 degrees. So let's make a triangle. 30 newtons, 30 degrees. There you go. Let's get some ink. 30 newtons, 30 degrees. This is the opposite side. This is the adjacent side. And if we do this correctly, we should remember cosine of 30 equals A over 30, and sine 30 equals O over 30, so we can get both of these sides. And if we do this, 30 times cosine 30 gives you the A, 30 times sine 30 gives you the O, and you should end up with 26 newtons here and 15 newtons here. And that's why this had to change from 20 to 15. And we'll see what that means in a second. So our applied force on this side, and go with me on this, we know that this situation, this is this, which means this is actually 15, and this is 26. So if I've got 26 going this way, which is actually negative 26, if I've got negative 26 going this way, my applied force has to be positive 26 going the other way. So from our tension is negative 26. Our y is positive 15. And that means that our applied force, because we know gravity is going to be 0, and our applied force is going straight across, so the y is going to be 0 on the applied. We know that the applied force, what minus 26 equals 0? 26. So the applied force must be 26. The y, well, what plus 15 equals 0? The gravity has to be 15, which is why this has to be 1.5, because if it's 15 newtons going down, 15 divided by 10 is 1.5, not 2. So that's kind of where I screwed up. But the tension, we already gave it to you as 30 newtons. There. So you can use one tension force to not only tell you what your applied force is in the x, but you can also use it to tell you what the gravitational force is in the y. And that's really important for the last problem in here. I'm sorry for screwing this up. If I just put 1.5 down, everything would have worked out correctly. If you just did the x variable, the x side, and you didn't care about the y, you still would have ended up in the same thing, and your FG would have been an FG of 20 newtons instead of 15, because that's what I originally put here. This would have been for 20 newtons going down. But if you do it right and you do the whole trigonometry and look at it, you should end up with 15 going down, 26 going across, and 30 going up to the corner. That's the last time I screwed up. So now here we are in our next problem, and we've got an applied force going into a wall and a floor at 30 degrees. We've got the applied force being 100 newtons, and we've got a 10 kilogram box. So I have a feeling we're going to have to do triangle again here. So I'll put our free body diagram there. And let's just name the forces. We'll start with, we know there's gravity. We know there's gravity. We know there's the applied force at 30 degrees, so I guess it would look more like that. If we're pushing something into a floor, the floor is holding it up, there's got to be some sort of a normal force. And if we're pushing it also into the wall, there's also got to be a normal force from the wall. So that's the arrows that your free body diagram should have, but now it's time to put in some numbers. So we got FG, we've got FA, we've got FN, and we've got FN also. So we'll call this normal force from the floor, we'll call this normal force from the wall. And we know the applied force is 100 newtons, and we know the gravitational force is also 100 newtons. I'll give that a negative there. Let's talk, again, I guess we should do XY. XY, normal force from the floor, normal force from the wall, gravity, and applied F net. 0 and 0. Alright, so let's get down what we can easily. We know the gravitational force is 0 in the X and negative 100 in the Y. We know the applied force is 100, but we also know that 100 is broken up in the X and the Y. So let's figure out what the magnitudes in the X and the Y are. So let's give ourselves a horizontal line, one of those. We'll do that. So we know the angle here is 30 newtons, or 30 degrees, and we know the applied force is 100 newtons. This would be my adjacent side, this would be my opposite, and that's going to be my hypotenuse. And if you do your trig correctly, you have the hypotenuse, you've got an angle, you can figure out the adjacent and the opposite using sine, cosine. And if you do this correctly, you should end up with this side being 87 newtons. You should end up with the opposite side being 50 newtons. So now we could say, well, it's positive 87 because it's going to the right, and negative 50 because it's going down. So my applied force is 87 and negative 50. So now it's time to look at the normal force and the force from the wall. Normal force from the floor is going straight up, so my x is going to be 0. And the normal force from the wall is going directly to the left, so I know my y is going to be 0. So the normal force from the wall is going to be what? Plus 0 plus 0 plus 87 gives me 0. That should be negative 87. And for my y, what plus negative 150 is going to give me 0? It's going to be positive 150. So remember how we said before, if you push down on something, you're going to make the floor work harder to keep it up. 150, and then negative 87. So that's your full free body diagram. You're going to have 150 going up, 87 to the left, 100 from gravity, and 100 from that applied force. You never really put the vertical and horizontal components into the free body diagram. All you want is that resultant force, or those resultant forces. And I'm just realizing on these, I probably didn't do as good of a job. Oh no, I guess I did. I was thinking I didn't remember putting negatives into these, but I did. So, now we're on to this one, and this one's actually not terrible. I'm allowing there to be friction, so let's give us a dot, and let's get some arrows going on here. We've got a applied force going up, we've got gravity going down, and I guess we're going to have friction going backwards, because there only seem to be one arrow, and we know friction, and that goes backwards. If we're pulling one way, friction is going to go opposite of it. We're dealing with 10 kilograms for the mass, so we know Fg is going to be negative 100. We know the applied force is going to be 30. And we know that the angle here is 30 newtons. So my suggestion, another XY chart. Let's go with our three forces. This guy's going to be friction. So force of friction, which we don't know. Force applied, which has both X and Y components, so we're going to have to resolve those. And Fg, which is negative 100 in the Y and 0 in the X. And we know we're going to add all these together. Net equals 0 and 0. Again, these are called statics because they're not accelerating. And sometimes statics don't move. So what are we going to figure out first? Should we do the applied force or the friction? We can't do the friction without knowing everything in the X dimension, which part of that applied force is there. So let's start it out. And then we'll probably figure one more thing out also. Actually, I should probably just say it now. There's a floor here. This thing is on the floor. It's not falling through the floor, so there's probably a normal force also. So let's put that up there. We don't know what that is either, so we're missing normal force of friction, but we've got some stuff to go by. And we know the beauty about the normal force is there's nothing going on in the X, and with friction there's nothing going on in the Y. So all we really have to do is figure out what's going on with the applied force, and then we can do a little bit of math, and we can probably figure some stuff out. So there's my hypotenuse, there's my adjacent side, there's my opposite side. This is 30 degrees, this is 30 newtons. Figuring out and using your trigonometry, you should come up with a 15 newtons going up and you should end up with 26 newtons going to the side. So your y component is going to be positive 15. Your x is going to be positive 26. So now 0 plus something plus 26 plus 0 equals 0. That's going to be a negative 26. And negative 100 plus 15 plus something equals 0. That's going to be positive 85. So our normal force is going to be 85 newtons going up. And our friction is going to be 26 newtons going to the left. So here's our full free body diagram. Gravity going down 100, applied force 30, normal force 85 up, and frictional force 26 to the left. Okay, and these are all in newtons. Sorry, I'm not labeling all of them. All right. And now, last but not least, this is a really good one because I don't tell you the mass. But if you remember, and here's a roadmap for it, this is only going in the x dimension, which means there's only one y, and that's the vertical component of this thing. So if you know what the y is going up, you know what the force of gravity is going down. If you know what the force of gravity is, just divide that by 10 and you should get your mass. So let's draw our free body diagram. We're dealing with tensions and no surfaces, so there's no normal force. So we're just dealing with gravity going down. We're dealing with the tension going that way. We're dealing with another tension going that way. We know this guy is 30 newtons. We know this guy is 15 newtons. So we need to figure out gravity, which will let us get the mass. Now, to do it, you have to be a little bit unorthodox. Just as I said, there's no y, which means if I can figure out what this is, I can figure out what that is. There's also no x. So if I know this is 15, I know this thing must be pulling with exactly 15 newtons going backwards. So think about it this way. Let's make our XY chart. I know I've got, I'm going to call this tension 1 and tension 2. FT1, FT2, FG, FNet. 2, 0, 0. I know that force of tension 2 is exactly positive 15 newtons, which means the force of tension 1 and 0 in the y, which means the tension on this thing must be negative 15 newtons. See where I'm going with this? So now I've got exactly how many sides of a triangle going on here. I've got this thing, and I've got this thing. I don't know an angle, but I don't need to because I have two sides of a right triangle. This is 30. This is 15. All I need to know is this. Because if I know this, then I know this, because they're equal but opposite. Well, how do I do, I got two sides of a right triangle, so I can do Pythagorean theorem. A squared plus b squared equals c squared. But this time, remember, the hypotenuse is c. I already have that. So we can do 15 squared plus b squared, because we'll say this is b, equals 30 squared. And you should end up with b squared equals 675. Because 30 squared is 900 and 15 squared is 225. So you subtract 225 from both sides, you get 675. Square root of 675 is going to give you b, which is 26. 26. So now I know that the tension, which is 30 newtons this way, is 15 newtons in the x, negative, and 26 newtons in the y, positive. So now, gravity only works in, oops, I put those in the wrong place. Sorry. It's negative 15 in the x and 26 in the y. My bad. So now, the 15 and the negative 15 equals 0. And that's a good thing because gravity also equals 0 in the x. But remember, gravity doesn't equal 0 on the y. Gravity is actually going to have to be negative 26 to get this whole thing to cancel out. So 26 in the y, 26 in the y, 15 in the x, 15 in the x. 26 here means F equals mg. 26 equals the mass times 10, which is the pull of gravity. So that means the mass is 2.6 kgs. So our mass is 2.6 kilograms. And that's how you can figure something's mass out, just by having a free body diagram that works. So, sorry for going backwards with just these. I switched them up. But other than that, this is exactly how you should attack this kind of problem. Hope that helped. I think that's the last one. So, hope you enjoyed this. Enjoy the rest of your weekend, and go Patriots.